Here are the solutions for worksheet 6. And for the first problem, this is right off of the exam, right, except the function is a little bit different. We need to figure out the values for a and b that are going to make our function continuous but not differentiable. So we actually need to first compute a derivative of f, and we're going to do it piecewise, right? So over here the derivative is going to be negative sine of x minus 1 if 1 is less than or equal to x. So if x is greater than 1, in other words. And over here for the second branch, the derivative is going to be 2ax plus b for x values less than 1. So let's see. If I want continuity, that means I want the left limit and the right limit to be the same. And since the function has continuous branches everywhere, then the left limit, which is for x values less than 1, is going to be, I just take this branch and I plug in 1 for x, so I get a plus b, and this should equal to the right limit, so I take this branch and I plug in 1 for x, which is just, it becomes cosine of 0, which is 1, and that's the limit from the right. So I end up with the equation a plus b equals 1, right? Now, since I want this to be not differentiable, I also have to look at a derivative and do the same thing. I want the derivative from the left, using this branch, to be different from the derivative from the right. And at 1, the derivative from the, let's say, f prime minus at 1, just some random notation here, is going to be, I plug in 1 for x, so I just get 2a plus b, and I want this to be different from the derivative from the right, and that's just going to be 0. So that's f prime from the right side at 1. That's because if I plug in 1 for x, sine of 0 becomes 0. Okay, so let's take a look now. What's the choice of a and b that are going to make this first equation work, and the second one also make it true? Well, I could take a equals a half and b equals a half, for example, right? And they are going to add up to 1. However, 2a plus b becomes 2 times a half is just 1 plus a half. This is definitely not 0, so we are okay. So this is a good choice for a and b. Now part b is asking us to find a and b that are going to make our function continuous and differentiable. So that means we have to solve the system a plus b equals 1, and at the same time 2a plus b equals 0, because we actually want the derivative from the left to equal the derivative from the right. That's what's going to make our function differentiable and continuous. So let's see, what can we do here? How about I take the first equation and I multiply it by negative 1, so I end up with negative a minus b equals minus 1. I copy down the second one, so 2a plus b equals 0. And let's see what happens if I add the 2. Over here I'm going to end up with just a equals minus 1. And when a equals negative 1, what do I have? I can take, say, this equation, so I have minus 1 plus b equals 1, which means then b is equal to 2. So these are the choices for a and b the unique choices that are going to make our function f both continuous and differentiable. Now part C is asking us to find a and b that are going to make the function differentiable but not continuous, and that's impossible. So
no, it's not possible, since f differentiable means f also has to be continuous.
now let's move on to the next problem. Let's see what we have here. We are asked to compute a few derivatives, and for the first one, f prime is going to be, well, first I bring down the 1/2, I copy down the inside, minus x squared. And I subtract 1 from the exponent 1/2, and that becomes 1/2 minus 1, so negative 1/2. But by chain rule now I have to multiply by the derivative of this inside, and that's going to be minus 2x from the square term plus 4 from the 4x term, and this constant has derivative 0. And another way to write that, I can just rewrite it as negative 2x plus 4 divided by twice square root of 3 plus 4x minus x squared. What about part B here? Again, we have to use chain rule because we have two functions composed. First one is a fifth power function. So f prime, because that's our outermost function, I bring down the 5 x over 1 plus x to the power 4, so I subtract 1 from my exponent, but now I have to multiply by the derivative of this inside. And notice that's a fraction, so the way to take the derivative here is I can just use quotient rule, right? So I take the derivative of the top, 1, times the bottom, minus the derivative of the bottom happens to be 1 as well, times the top, all over the bottom squared, just like so. And so this is 5
x over 1 plus x to the 4th. Here I have 1 plus x minus x, so I just have 1 over 1 plus x squared. And I could go a little bit further and combine these to get a 1 plus x to the 6, but it's not really necessary. The whole point of this problem is to make sure we can apply the chain rule correctly, and as well as the quotient rule. Okay, how about the next one? Over here, automatically we notice this is a product of two functions, so I have to use product rule. And f prime then is going to be the derivative of the first, so the derivative of 2x squared becomes 4x times the second unchanged, 2 minus x, plus now the first function, so 2x squared, and I know that the derivative of, say, square root of x is going to be 1 over twice the root, so I get 1 over twice the root of 2 minus x, but I have now this 2 minus x here, which is the inside function, so I have to multiply by its derivative, which is negative 1. So I can just put the negative right there, and I'm done. How about part D? Well, let's see. Again, we have a product of two functions, so I'm going to use product rule. So f prime then is going to become derivative of the first, which is 4 x squared plus 3 quantity cubed, because I subtract 1 from the exponent, but I also have to apply chain rule here, so times 2x, which is the derivative of the x squared plus 3 part,
times the second function unchanged. So that's 2x cubed minus 5 quantity cubed, right? Plus now, I take the derivative of the second, so that becomes 2x cubed minus 5 squared by subtracting 1 from the exponent, times the derivative of the inside, so 6x times the first function unchanged, so x squared plus 3 to the fourth. And that's the whole derivative there. Okay, how about problem 3? Over here we have quite a composition of functions, and I have some products inside too. So let's see, how do we do this derivative? F prime is going to be, okay, the outermost function is cosine, and its derivative is negative sine of whatever I have inside here. So that's x times sine of x tangent x. But now I have to start applying chain rule. So I have to multiply now by the derivative of this inside. So I take the derivative of the first, which is x, right? I have a product of these two guys. So I take the derivative of x, that's 1 times the sine part, x tangent x, plus now the first times the derivative of the second. And again I have a trig function here. Outermost is sine, so its derivative is cosine of whatever I have inside. However, now this inside part is again a function, so I have to multiply finally by its derivative. And again I have another product rule that I have to undo. Okay, so that's derivative first. This is 1 tangent x plus x secant squared x. So that is the derivative of x tangent x. This whole piece was a derivative of the sine of x tangent x. So that finishes off my problem. Right, so it's quite complicated looking and quite a few steps involved. You got to be able to keep track of all of the nesting that's going on here to get the correct answer. Alright, let's move on to problem 4. And problem 4 is asking us to use implicit differentiation to compute the following derivatives. Right? First, we need to find dy dx for the equation 2y squared equals y plus x. So let's take this equation and take the derivative with respect to x, because I want to find dy with respect to x here. I'm going to be treating y as a function of x. So over here I get 4y, and from chain rule I get dy dx equals derivative of y is dy dx plus 1, which is the derivative of x with respect to x. I'm going to move all of the terms that have the derivative attached to them on the left side, and I'll factor the dy dx. So I'm left with 4y, and then this is like a 1, but moving it over becomes a negative 1 equals 1. So that means if I solve for dy dx, I end up with 1 over 4y minus 1. So that should be the answer there. Now part B is asking us for the same equation to find now dx dy. So that means I'm going to differentiate this with respect to y, treating x as a function of y. On the left hand side I end up with simply 4y squared, and since I'm taking the derivative, 4y to the first, not y squared, and since I'm taking the derivative with respect to y, then that means I don't have to apply chain rule anymore. And then on the right hand plus dx
dy. Y coming from the derivative of y, x then becomes dx dy. And this one is a little bit easier to solve. I just solve for dx dy, but there's nothing to factor. I just have to move the 1 to the other side. So I get dx dy equals 4y minus the 1 there. And notice these are very similar looking, except one of them is the reciprocal of the other. And that makes sense, right? We know just kind of intuitively when we work with these differentials, we can treat them as fractions, and if I take dy dx and I want to find dx dy, I simply take the reciprocal of that. So that's a shortcut to use on, say, future quizzes if you have to deal with like a multiple choice question. Okay, how about this next one? We're asked to find y prime for that equation. So let's take the derivative with respect to x, because I'm finding y prime of x, which is the same as dy dx. And if I take that derivative with respect to x, I get 2x. Now I have a product, so I get minus 1 y minus x dy dx, and plus 2y dy dx equals the derivative of the constant becomes 0. Move everything that doesn't have dy dx to the other side, and factor out the dy dx from these two terms to end up with dy dx negative x plus 2y equals, and I'll just flip the order because I don't want to write negative y. I'll simply write y minus 2x, and if I divide through by this term, I get that dy dx is going to be y minus 2x over 2y minus x. So that's y prime of x. Now, for the same equation, since we have to find x prime of y, I can use the shortcut that I was talking about earlier, or I can do it the long way. But either way, I should get the answer dx dy equals the reciprocal of this. So I should have 2y minus x over y minus 2x. Now problem 5 is a little bit different. So we're given an equation that relates x, y, and t, and we are asked to find a derivative, or just we're that y and x are both functions of t. In other words, every time I take the derivative of x or y with respect to t, I have to apply some sort of chain rule depending on which one I'm using. So let's go ahead and do it. First, I have a product rule here because I have x and y multiplied. So the derivative of the first is 3x squared times dx dt, and that becomes dx dt is just cosine t, that's the derivative of sine, times, copy down, y, plus the second part of the product rule is x cubed, and then dy dt now is going to be 3t squared. And now I have something similar going on here. So that's the first product rule. I have another product rule to do over here. The first is dx dt, right? 1 times dx dt, so I have just cosine t times y cubed plus the first times the derivative of the second. So x times 3y squared
dy dt, which is now 3t squared. So that finishes off the left-hand side, and on the right-hand side I just take the derivative of t squared with respect to t, so I end up with just 2t. And I'm not going to simplify this, right? The whole point was just take the derivative with respect to t and leave it as is, but this is what it should look like, right? So I have a product rule here expanding into this, product rule here expanding into that, and right-hand side is very simple. Here we have a few word problems now. The first one is about a circle, and I'm given that its radius is changing at a positive rate, which means it's increasing, of dr dt is that, plus 2 centimeters per second. And we're asked, how fast is the area changing when time is 2? Well, first we need an equation that relates the area of the circle and the radius, and I know that that is a equals pi r squared, right? A meaning the area, r meaning the radius. And if I'm trying to find how fast the area is changing when time is 2, that means I'm looking for dA dt. So let's take this equation now and take the derivative of it with respect to t, just like we did in problem 5, right? It's the same idea. So I'm treating a and r as functions of t. On the left-hand side, I end up with just dA dt, and this should equal now 2 pi r, the 2 coming from the exponent of r, times, now from chain rule, because r is a function of t, times dr dt. Now, let's see, what do we know here? I know that dA dt is what I'm trying to find, right? So I'm not sure what this is going to be. I know that this is given to me, this is equal to 2. I don't know r, so I think actually the problem should ask, okay, how fast is the area changing when r is equal to 2? Otherwise we can't really determine this. So let's go ahead and plug in what we know. So this is 2, this is 2, so that means dA dt is what? 2 pi 2 times 2, so that becomes 8 pi, and that's positive, so that means it's increasing, and the units are going to be centimeters squared per second, right? The unit of area, but it's a change in area, so it's per second because the change happens with respect to time there. Okay, how about problem 7? So I have a spherical balloon, in other words a sphere, that is filling up with air at a rate of 5 cubic centimeters per second. Now let's translate that into math, right? It's filling up with air, so the volume of the balloon increases at this rate. So automatically I get the equation dV dt, where V is the volume, should be 5, positive because it's filling up, right? So increasing centimeters cubed per second. And we're asked, okay, how fast is the radius of the balloon changing when t is 2? And I think, again, just like in the previous problem, when r is 2, is what this question was trying to say. So let's write up an equation. In fact, we're given one. We're given an equation that relates radius and volume together. So I have V equals to 4/3 pi r cubed. And let's take this and take the derivative of it with respect to t. So I get dV dt equals, well, the 3 is going to come down, canceling this 3 in the denominator. So I'm left with just 4 pi r squared, but because both the radius and the volume are changing with respect to t, I have to multiply this by dr dt. Now, notice the question was, how fast is the radius of the balloon changing? So this is what we're trying to find, right? We're trying to figure out what is dr dt. And we want that when the radius, not t, but when r is equal to 2. Well, it's very simple. I know dv dt is 5, so I have the equation 5 equals 4 times 2 is 8 pi dr dt, and I'm trying to solve for that, so just divide by 8 pi. So dr dt is going to then be equal to 5 over 8 pi. Oh, I'm sorry, I made the mistake. That's r squared, so 4 times 4 should be 16. So 5 over 16 pi is the correct answer. Okay, how about the last, not the last, but problem 8. So I'm given the position of a particle in terms of, I guess I meant to write this in terms of t, not in terms of x. So let's say x means time here. And it's asking us, is there ever a time during the first second of the motion where the particle is at rest? In other words, what does particle at rest mean? That means the velocity is equal to 0. Okay, so let's go ahead and figure this out. So if that's the position function, the velocity, and you know what, I'll actually keep it in terms of t. So instead of x, I'll use t, because that's the variable we're going to use for time. I take the derivative, right, because that's how the position and the velocity are related. And the 5 comes down, canceling the 1/5. So I get x to the 4th minus, and not x, t again, minus 4t plus 1. So this is the velocity function. And if solution to this
equation being equal to 0 in the first second, so I'm trying to figure out between 0 and 1, are there any solutions? And I actually recognize this from one of the previous problems, right? We had the same type of function, so I know, this was on the quiz, I know that yes, there is a solution. And to see that, I simply take v of 0, which is going to become 1, and v of 1, which is going to become minus 2. And because that's greater than 0 and that's less than 0, I know that by intermediate value theorem, there is some point where v of t is 0 for some t inside my interval 0, 1. Okay, so yes, there is a time when that happens. The last problem, again, I'm given the position of a particle in terms of time again, and I'm asked for what non-negative values of t is the particle at rest. So again, particle at rest means the velocity is 0. So let's figure out what the velocity is. V of t is going to be the derivative of the position function, so s prime of t, and this is a very simple derivative. The derivative of cosine is negative sine. Negative times a negative becomes positive sine of pi t, and that's divided by 2 pi, but I have to multiply by the derivative of the inside, which is just pi. So that's the same as sine of pi t over 2. And I want to figure out, where is this 0? Now I know
from the graph of sine for positive values of t that sine is 0 at 0, at pi, at 2 pi, 3 pi, and so on, integer
multiples of pi, right? And since over here the variable is pi t, I want pi t to be an integer multiple of pi, right? So this means that for any t that is 0, 1, 2 is going to work. In other words, for every non-negative integer. And that's the solutions for the entire worksheet.